This is SpaceTime, Series 22, Episode 7. Coming up on SpaceTime, a strange new phenomenon cowers astronomers, a new way of studying mysterious dark matter, and new revelation shows Saturn's rings are relatively recent. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The American Astronomical Society's meeting in Seattle, Washington has been told scientists are still hotly debating the details of AT2018 Cow, a strange and powerful explosive phenomenon bright enough to be seen throughout the visible universe. Located some 200 million light-years away in the direction of the constellation Hercules, AT2018 Cow was immediately nicknamed the Cow based on the final 3 letters of its catalogue name. The strange cosmic explosion, discovered by the Atlas All-Sky Survey System in Hawaii on June the 16th last year, is unlike anything ever seen before. Immediately after receiving the alert, an international research team led by Raffaella Magutti from Northwestern University leapt into action and began observing the unusual source across the electromagnetic spectrum, at X-ray, optical, infrared and radio wavelengths, measuring its changing characteristics. Telescopes around the world contributed to the effort, using spectroscopy to try and decode the nature of the source. Among the telescopes contributing to the study was the Southern Astrophysical Research Telescope in Chile, whose instruments obtained the initial spectra of the Cow. The spectra showed matter was expanding from the object at up to 10% the speed of light. Yet, despite more than half a year of study, using both ground and space-based observatories, scientists are still unsure about exactly what it is they've seen. The 2 leading hypotheses are either a very unusual supernova, that is, exploding star, or the shredding of a star that's passed too close to a black hole, a so-called tidal disruption event. The problem is this object's characteristics don't really match any previously seen examples of either event. If it's a supernova, then it's unlike any supernova ever seen before. Supernova explosions are so bright they can briefly outshine the galaxies they're in. Yet this event was unusually bright even for a supernova, and it was intrinsically brighter at its peak. On top of that, it brightened and then faded much faster than what would be expected from a supernova. Also, the object spectrum didn't look like a supernova event, and it was far brighter in millimeter wavelengths than any other supernova ever observed. When stars far more massive than the Sun explode in supernovae at the end of their lives, usually no central engine is produced. However, if the progenitor star is massive enough, it could produce a hypernova rather than a supernova, which could then produce a gamma ray burst, generating superfast jets of material emitting gamma rays. The thing is, gamma ray bursts usually only last for a few milliseconds, maybe a few seconds at most for a long-duration gamma ray burst. But the event powering AT2018 Cow lasted for several weeks. Most astronomers agree that AT2018 Cow's behavior requires some sort of central source of ongoing energy, quite unlike those of a supernova explosion. So, what about the other option, a tidal disruption event? Well, the thing is, the Cow also differed from previously seen tidal disruption events. In the case of a tidal disruption event, the central engine would come to life as the black hole accreted material from the star being shredded by its gravitational pull. But this event is off-center from its host galaxy, meaning it's not a star being shredded by the supermassive black hole at the center of a galaxy. Of course, it could be a tidal disruption event caused by an intermediate mass black hole somewhere else in the host galaxy. But the thing is, these intermediate-sized black holes usually form in stellar clusters, while AT2018 Cow appears to be inside a high-density interstellar medium, which makes it difficult to reconcile with the gas density in stellar clusters. Still, if it is a black hole that's drawing material from its surroundings, then the inflowing material is forming a rotating disk around the black hole, the accretion disk, and that disk radiates prolific amounts of energy. This is the type of central engine which powers quasars and radio galaxies across the universe. Reporting in the Astrophysical Journal, McGoody believes this event may be signifying the exact moment of the birth of either a nascent stellar mass black hole or a rapidly rotating neutron star with an extremely powerful magnetic field, in other words, a magnetar. Astronomers know from theory that both stellar mass black holes and neutron stars form when massive stars die in unusually powerful supernova or hypernova explosions, but they've never seen one of these events right at the moment of birth. So this event may represent a new class of objects within the category known as fast luminous transients. If that's the case, then it will be the first time astronomers have actually witnessed the birth of a magnetar. The central energy source, that central engine we talked about, could be a powerful shock wave hitting a dense shell of material near the object's core. However, because of AT 2018 Cow's strange behaviour, the ultimate verdict is still unclear. This is SpaceTime. I'm Stuart Gary. Astronomers have developed a new method of using starlight to study the nature of dark matter. Dark matter is a mysterious substance, and understanding it remains one of the biggest questions in science today. But it is an important question to answer because dark matter makes up some 80% of all the mass in the universe, and it plays a crucial role in holding stars together in galaxies. Yet scientists know virtually nothing about it. You see, dark matter is invisible, so it can only be identified by its gravitational interaction with normal or baryonic matter. That's the stuff that makes up the stars, planets, buildings, cars, trees, and people in the world around us. This new research, being reported in the monthly notices of the Royal Astronomical Society, maps the location of dark matter by studying how it affects the light from rogue stars in galaxy clusters. Rogue stars are ones that have been pulled out of their original host galaxies by the gravitational tidal interactions of other galaxies inside huge collections of hundreds to thousands of galaxies, all drawn together by gravity and collectively known as galaxy clusters. The study's lead author, Dr. Maria Montez from the University of New South Wales, says it's possible to sort of indirectly see dark matter by examining the faint glow of starlight that exists in galaxy clusters, known as intracluster light. Intracluster light is made up of stars that do not belong to any one specific galaxy, singled out because they move differently compared to stars in galaxies. Instead, these stars float freely within the cluster. Now, as you travel away from the center of a galaxy towards its outskirts, it becomes increasingly dominated by dark matter, and this is also where you find intracluster light. This faint glow of the stars accurately traces the distribution of dark matter, and so may be able to help astronomers explore the very nature of this mysterious element of the universe. Montez's study is the first to confirm the potential of intracluster light in mapping dark matter with current imaging data. Previous studies have examined the reach of intracluster light in galaxy clusters, but Montez's study shows intracluster light can indicate the actual distribution of dark matter. Montez says intracluster light traces the distribution of mass extremely well, thereby highlighting the dark matter in a galaxy cluster. So this means astronomers now have a luminous tracer of this dark matter and how it's distributed in clusters of galaxies. Montez used publicly available deep imaging data from the Hubble Frontier Fields Initiative, an ambitious plan to test the limits of the Hubble Space Telescope by pointing it towards deep space to take images of galaxy clusters billions upon billions of light years away. The result of this initiative has been some of the most amazing images of the universe. The 6 galaxy clusters Montez studied are among the most distant objects ever photographed by Hubble. Until now, dark matter analysis has been achieved through study of a phenomenon called gravitational lensing. First postulated by Albert Einstein, gravitational lensing works by bending or lensing light. A cluster of galaxies can act as a lens, bending light from more distant galaxies. And by studying this stretching of light, it's possible to map dark matter in a galaxy cluster. However, this analytical process is hard to measure, and observing the intracluster light is easier. To test the idea, Montez and colleagues mapped the distribution of intracluster light and then compared it with the distribution of mass in the cluster. With this new method, exploring the distribution of dark matter in galaxy clusters in detail can be done with just deep imaging observations, thereby bypassing gravitational lensing. Now, it won't replace gravitational lensing, but it can be used as an additional valuable technique to help refine existing mass maps. It means astronomers can now see how dark matter is being distributed and then compare this distribution with the results from supercomputer cosmological simulations. The authors are now focusing on additional clusters to see if the match between dark matter and intracluster light holds up. Montez says it can help the gravitational lensing community upgrade their mass maps, and consequently, it will help science understand the nature of dark matter.
Basically, for a long time, I've been studying this very diffuse light. It's called intracluster light. So this light comes from, it's a product of the interactions between galaxies in the cluster. Because of these interactions, individual stars are stripped from their host galaxies, from the galaxies they live in, and end up floating freely in the cluster.
By looking at these free-floating stars, you get an idea of what the dark matter is doing.
Yeah. Exactly. It's what we found in this study. We found that basically studying how this light distributes in the cluster of galaxies, we found that the distribution of this light is very similar to the distribution of the dark matter in the cluster.
And which clusters did you look at?
So I looked at 6 clusters. That is a survey that made with the Hubble Space Telescope, and the survey is called Frontier Fields. They are the deepest images of clusters ever observed by the Hubble Space Telescope, which for me it's perfect because I study this intracluster light and it's a very, very, very faint light. So yeah, those images were perfect for what I've been doing.
And galaxy clusters, these are the largest structures in the universe.
Yeah, the largest structures gravitationally bound.
Does it look like the dark matter halos surrounding the individual galaxies in these clusters, that's all merged together, has it? What are you seeing?
So basically, in galaxy clusters, basically what you see is it's the global dark matter halo.
For the whole cluster?
For the whole cluster, yes. And if you study how, how it distributes, how this distribution, how the substructures of the galaxy cluster, you observe more or less substructure, you can infer the nature of the dark matter. So that makes, normally, studying the distribution of dark matter in clusters of galaxies is done with gravitational lensing, which means that you see like a background source, that it's basically the galaxy clusters act like lenses to these background galaxies. So you will see these background galaxies brighter, a little bit distorted. So basically, if you understand how the distribution of matter in the cluster you can basically...
You're using the gravitationally lensed light from the background galaxy to infer the structure of the foreground galaxy cluster.
Yeah, basically it's what people have been doing till now, but the thing is that this process is a little bit time-consuming because you need like very deep images to see all these background galaxies, and also you need to know where those galaxies are. You need a spectrum of those background galaxies. So you have to have those two things. But with the work that we've been doing, because we only study, these deep images, we only need deep images to understand how the dark matter is distributed in clusters of galaxies. Because what we've been doing is comparing how this intercluster light compares with the previous maps of mass of those clusters that have been published. Now that we know that, we can basically study more galaxy clusters because our methodology is more efficient, and we can start, seeing if tracing is not perfect, we can infer some properties of the dark matter, or, we can start studying things in a more statistical way.
We know dark matter appears to react with the baryonic matter in our universe only through gravity. And basically what you're doing is confirming that is the situation and that there aren't any differences in the way gravity acts with dark matter compared to normal matter.
So far, no, but we are a little bit limited by the mass maps.
Yep.
Derived by gravitational lensing. So basically what we want to do is extend these studies, confirm this also with simulations. By the way, I know that it's been confirmed, but we are waiting for the article to be published. But basically, like any deviation from this diffuse light to the dark matter will tell us a lot about the nature of the dark matter.
Every little clue, every little idiosyncrasy with dark matter tells us something new about its properties.
Yeah. The thing is that so far we cannot tell anything about dark matter, anything else,
That's Dr. Maria Montez from the University of New South Wales. I'm Stuart Gary, and this is SpaceTime. New data from NASA's Cassini mission indicates Saturn's iconic rings are a relatively recent addition to the majestic gas giant. The new findings, reported in the journal Science, show that Saturn's rings only formed between 10 million and 100 million years ago. The findings are based on a new analysis of gravity science data gleaned from measurements collected during the final ultra-close orbits of Cassini, performed in 2017 as the spacecraft neared the end of its historic mission. The planet Saturn formed about 4.6 billion years ago in the early years of the solar system. There have always been lots of theories suggesting that planetary ring systems are relatively ephemeral features, lasting just a few tens of millions of years before slowly fading away. But as to how long they really last and how long Saturn's had her rings, well, no one's ever been really sure. To figure out the age of Saturn's rings, scientists needed to measure something else, the mass of the rings, or how much material they hold. Researchers already had remote sensing measurements from Cassini, as well as from both of NASA's Voyager spacecraft from the early 1980s. But then came Cassini's unprecedented up-close data from its final orbits. As the spacecraft was running out of fuel, NASA's Jet Propulsion Laboratory in Pasadena, California, which operated Cassini, performed a series of 22 dives between the planet and its rings. These dives allowed the spacecraft to test Saturn's gravity field, where it could feel both the tug of the planet and the rings. Radio signals sent to Cassini from the antennas of NASA's Deep Space Network and the European Space Agency relayed the spacecraft's velocity and acceleration and how that changed as a result of differing gravitational effects. Once scientists knew just how much gravity was pulling on Cassini and causing it to accelerate down to just a fraction of a millimeter per second, they could then determine how massive the planet was and how massive its rings were. The study's lead author, Luciano Les from the Sapienza University of Rome, says only by getting so close to Saturn in Cassini's final orbits were scientists able to gather the measurements they needed to work out the details. The data allowed Cassini to complete one of the fundamental goals of its mission, not only to determine the mass of the rings, but to use that information to refine models to determine the age of the rings as well. The new findings build on a connection scientists previously made between the mass of the rings and their age. You see, low mass points to a younger age, because the rings, which are bright and mostly made of ice, would have been contaminated and darkened by interplanetary debris over a longer period. With a better calculation of ring mass, scientists were better able to estimate ring age. But it's not over yet. Scientists will continue working to try and figure out how the rings actually formed. The new evidence of young rings lends credence to theories that they formed either from a comet that wandered too close and was torn apart by Saturn's gravity, or by an event which broke up an earlier generation of icy moons. From Cassini's super-close vantage point, immersed in Saturn's gravity field, the spacecraft relayed measurements that led scientists to another surprising discovery. It's long been known that Saturn's equatorial atmosphere rotates around the planet faster than its inner layers and core. Think of a set of nested cylinders all rotating at different speeds. Eventually, towards the center of the planet, the layers all move in synchrony and rotate together. Jupiter's atmosphere behaves in the same way. But these new findings show that Saturn's cloud layers start rotating in synchrony much deeper into the planet, at least 9,000 kilometers in. That's some 3 times deeper than the same phenomenon on Jupiter. In fact, it's a depth that equals about 15% of Saturn's entire radius. Cassini project scientist Linda Spilker from JPL says the discovery of deeply rotating layers is a surprising revelation about the internal structure of Saturn. The questions are, what's causing the more rapid rotating part of the atmosphere to go so deep, and what does that tell us about Saturn's interior? At the same time, this measurement of Saturn's gravity has solved yet another unknown, the mass of the core. Models of the interior developed by co-author Professor Burkhard Militzer from the University of California, Berkeley, indicate that Saturn's core is somewhere between 15 and 18 times the mass of the Earth. Cassini's mission ended in September 2017, when it was low on fuel, virtually flying on vapors, and was deliberately plunged into Saturn's atmosphere in order to protect the planet's moons, some of which could harbour life, from the potential of Earth contamination. I'm Stuart Gary. You're listening to SpaceTime. Iran has failed in its bid to place its 90-kilogram Payam surveillance satellite into orbit. Tehran says the Seymour rocket used for the flight suffered a failure with its third stage, preventing it from reaching orbit. The launch attempt from the Imam Khomeini Space Center in Iran's Semnan province came despite warnings from Washington that in reality the mission was nothing but a cover for testing an Iranian intercontinental ballistic missile. As previous Seymour launch vehicles only had 2 stages, this failed mission suggests Tehran was using the flight to test a new upper third stage. Also known as the Shafir-2, the 27-metre-tall Seymour, Farsi for Phoenix, uses a North Korean-developed first stage called the Una, which is equipped with 4 Scud missile rocket motors. The Seymour's second stage is a modified Shahab-3 medium-range ballistic missile. The Shahab-3 is actually a North Korean Nodong-1 missile, which was developed by Pyongyang using Soviet-sourced Egyptian Scud-B and Chinese Scud-C missile technology. The Shahab-3 has a range of over 2,000 kilometres, delivering either a single 1,200 kilogram warhead or 5 MIRV, or independently targetable multiple re-entry vehicle warheads. The International Atomic Energy Agency says that during the early 2000s, the Islamic Republic may have explored various fusing, aiming and firing systems designed to make the Shahab-3 more capable of reliably delivering a nuclear warhead. In fact, US Secretary of State Mike Pompeo says Tehran's space program is simply serving as a cover to develop missiles capable of carrying nuclear warheads to the mainland United States. Pompeo says such rocket launches violate United Nations Security Council Resolution 2231, which endorsed the 2015 nuclear deal between Iran and world powers, calling on Tehran to refrain from undertaking activities related to ballistic missiles capable of delivering nuclear weapons, including launches. Last May, US President Donald Trump pulled out of the Iran nuclear deal, citing multiple violations by Tehran, including its sponsorship of terrorist organizations such as Hezbollah and Hamas, and continuing to secretly develop nuclear weapons. However, the oil-rich nation insists its nuclear program is for peaceful power generation only. SpaceX has successfully launched the 8th and final batch of Iridium Next telecommunications satellites into orbit. The spacecraft were released an hour and 12 minutes after launch from the Vandenberg Air Force Base in California.
9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Liftoff of Falcon 9.
Vehicles pitching downrange.
Stage 1 props nominal.
T plus 40 seconds and Falcon 9 is on its way with a countdown of the last 10 seconds by Iridium CEO Matt Desch. We're throttling down now in preparation for the period of maximum dynamic pressure.
Vehicle supersonic.
Garcia on countdown 1, first motion time 15:31:33.492 UTC.
Calling out the time there of liftoff over the net.
Position of signal.
We're through the period of maximum dynamic pressure.
Maximum aerodynamic pressure.
Merlin engines continuing to perform at 1.7 million pounds of thrust. Falcon 9 heading out into the upper atmosphere. We're headed south from Vandenberg Air Force Base, Space Launch Complex 4 East.
MVAC engine chill.
The MVAC engine cheer call out indicates that we have now opened up the oxygen that goes to the pump on the second stage engine, chilling it down for ignition coming up about a minute from now. We're hearing good call outs. Propulsion looks nominal. The trajectory looks good. Now coming up will be rapid fire events. Main engine cutoff. We shut down the 9 Merlin 1D engines. At 2.5 minutes, we will separate the stages. We'll light the second stage engine. And at just a little bit after that, we'll relight 3 engines on the first stage to begin slowing it down for a landing in the Pacific Ocean on our drone ship.
Stage separation confirmed. MVAC ignition.
Stage 1 has entered its flip.
So we've had successful shutdown of the first stage. It's separated. It's doing the flip to reorient, and it's lit its 3 engines to begin slowing it down to come to the drone ship. Meanwhile, on second stage engine has ignited. Begin propelling the Iridium satellites as we get ready for fairing separation.
Fairing separation confirmed. Stage 1 boost back shutdown.
A lot of events happening. The fairing separate. We've had shutdown from the boost back burn and titanium grid fins slowly extending. That's nominal for those grid fins. Attitude control gas, nitrogen, that's used to orient the first stage. We're coming up 4 minutes into flight. In about a minute and a half, the first stage will initiate a quick re-entry burn to again slow the rocket down as it re-enters Earth's atmosphere. A minute later, we'll perform the final burn, the landing burn, which will decelerate the vehicle to a gentle landing atop our drone ship. Just read the instructions. Now, as a reminder, recovery is always a secondary objective to our primary goal of delivering our customers' satellites to orbit. MVAC-D second stage engine running about 200,000 pounds of thrust in the vacuum of space, the nozzle glowing red hot. That's nominal for that nozzle. We're about half a minute away from the entry burn. This one will also be a 3-engine burn. That'll slow the vehicle down as we go to subsonic speeds, and then eventually a final burn a little bit after that to land on the drone ship.
Stage 1 entry burn is started.
Call out the entry burn on stage 1 is started. 3 engines up and running.
Stage 1 entry burn shut down.
And the entry burn shut down called out over the countdown net, as you heard.
Stage 1 FTS is saved.
Everything continuing to look good. First stage entry burn has ended. We're less than a minute until the third and final landing burn, followed by touchdown on the drone ship. The first stage descending back down through the atmosphere as it's coming up on the cloud deck.
Drone ship AOS.
Drone ship AOS means the drone ship has acquired
Stage
the
1
signal.
landing burn is started.
Center engine has lit. We're slowing ourselves down, preparing to find the drone ship right underneath us. And we're getting the signal dropout, which is not unusual.
Following main engine cutout and stage separation, the first stage of the Falcon 9 successfully returned to Earth, landing on the SpaceX drone ship. Just read the instructions, which had been pre-positioned downrange in the North Pacific Ocean.
Falcon 9 has landed. Landing operators moving to 11.1
There you go. We heard the call out from recovery. Falcon 9 has landed on the deck of the drone ship. We can confirm we're down with the first stage. We're pressing on the second stage mission. Currently, trajectory looks good. We've begun throttling down the Merlin vacuum engine, maintaining the G-load on the Iridium Next satellite.
The 10-satellite payload means all 75 Iridium next-generation telecommunications satellites are now in orbit. The Iridium satellite constellation circles the planet with 11 satellites in each of 6 orbital planes, providing direct-to-phone mobile satellite communications. After launching a record 39 rockets into orbit during 2018, Beijing has kicked off its 2019 space campaign with the flight of the ChinaSat 2D military communications satellite. The ChinaSat, or Zhongjing 2D, was flown aboard a Long March 3B rocket launched from the Zhaichang Satellite Launch Center in southwestern China's Sichuan province. The Zhongjing 2D is a Shengtong series geostationary military communications satellite. It's designed to provide secure digital data and voice communication for the Chinese military using Ku-band transponders. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns that infections of the superbug golden staph are on the rise in communities in Victoria and Western Australia. The findings, reported in the Medical Journal of Australia, shows that while there's a decline in Staphylococcus aureus, the superbug which causes golden staph infections in hospitals over the past few years, the numbers are on the rise for golden staph infections acquired outside hospitals. Between the start of 2011 and the end of 2016, the dangerous bloodstream infection increased in the community by 8% per year in Victoria and by 6% per year in Western Australia. A new Rutgers study has found that 9/11 World Trade Center first responders are still at an increased risk for both head and neck cancers. A report in the International Journal of Cancer found a significant increase in cancers among workers and volunteers who responded to the 9/11 terrorist attacks on the World Trade Center. The findings are pointing to newly emerging risks that require ongoing monitoring and treatment for those who were exposed during the initial response. Scientists found a 40% increase in diagnosis of these cancers between 2009 and 2012. The findings highlight the need to examine the potentially carcinogenic effects of World Trade Center exposure in the context of other strong risk factors and the need for continued medical monitoring of responders, especially police, fire department and military. 2,996 people were killed and more than 6,000 others injured when Islamic militants with the Al-Qaeda terrorist group hijacked 4 commercial airliners, flying 2 of them into the Twin Towers of the World Trade Center in New York City and a 3rd into the Pentagon in Arlington, Virginia. A 4th hijacked airliner believed to be destined for the White House crashed into a field near Shanksville, Pennsylvania, after passengers and crew thwarted the terrorists' plans. A new study has found that physical activity, weight and height may influence female lifespans far more than male lifespans. A report in the British Medical Journal based on an observational study has found that women taller than 175 centimetres were 31% more likely to live to the age of 90 compared to women shorter than 160 centimetres. There was no similar association between height and lifespan among males. For physical activity, it seems 60 minutes of daily exercise is the optimal time that increases a woman's likelihood of living to the age of 90. However, men have to work out far longer, some 90 minutes plus, in order to increase their chances of living for 90 years. Well, if you need that cup of joe to get started in the morning, we've got some bad news for you. A 20-year study reported in the journal Science Advances has found that 60% of all wild coffee species are now at a high risk of extinction due to increasing droughts, shrinking forests, and the spread of deadly pests. Scientists warn that losing these wild species poses a serious threat to the coffee production industry, which is dominated by just 2 varieties, Arabica, which is susceptible to high temperatures, and Robusta, which is sensitive to dry soils. The wild species are needed to provide the genetic diversity needed to boost the viability of commercial plants in the face of climate change. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.